Section 9.3 starts with significant tests using a population mean. These are connected to, once again, confidence intervals, and so a lot of the same calculations and a lot of the same conditions apply. We're going to go ahead and stick with just significance test on this one. We'll come back to the other ones in a future lecture. So confidence intervals for population proportions are based on finding our z-score for the test statistic, and as our test statistic actually, and looking to the extreme of that, or both extremes if we're talking about a two-tailed test, and we're using a standard normal distribution. For a population mean, very rarely do we have the standard deviation of the population, so we have to use the standard deviation of the sample, which is calculated like that. And those standard deviations, the distribution of those do not approximate a normal curve, but a t-distribution. Then you have to pay attention to the degrees of freedom, which is the sample size -1, because the distribution is very different. Because of that, we're going to have to use our t-values when we do a significance test, just like we did when we constructed confidence intervals in section 8.3. In an earlier example, we looked at a company that had created some new AAA batteries, and they thought they lasted longer than their regular ones. So they knew that their regular batteries lasted for about 30 hours of continuous use on average. And they took an SRS of 15 new batteries, and those lasted an average of 33.9 with a standard deviation of 9.8. We're going to go ahead and run a significance test to find out if this data gives convincing evidence that the new batteries last longer on average. So our null, of course, is going to be the accepted thing over time, which is the 30 hours of continuous use. And then we're looking based, they thought that they've lasted longer, so we're going to do a one-tail test looking at the from the test statistic to the right, because we're looking at greater than. We're going to be doing the same exact conditions that we would use for a confidence interval, we would use for a significance test for a mean, and the conditions are very similar to the ones for the proportion. So you're going to always make sure that the data comes from a well-designed random sample or randomized experiment. You're going to make sure that if you multiply 10 times the n, it's going to be less than or equal to the population itself. And then here's where it's just a little different. If the population has a normal distribution or the sample size is larger than 30, we're going to go ahead and use t-scores, assuming we don't have the population standard deviation. Now, if the population distribution is an unknown shape and n is less than 30, we actually have to check to see if there's strong skewness or outliers. So we will graph it and look at that. And if so, because the population has to be normal for us to be able to use t-scores. So when we calculate our z-score or we calculate our t-score, we're finding how far our statistic is away from the parameter value, away from our null value. So our test statistic always comes from, here is our information from our sample, here's our information from the null, and then our standard deviation of the statistic. When we have a mean as our statistic, we almost always are going to have to find our standard deviation using the standard deviation of the sample itself. So for our test, the null hypothesis is the population mean is going to go ahead and be our null, And our statistic is the sample mean, and the standard deviation, once again, has to be our sample standard deviation because we rarely have the population standard deviation. So the resulting test statistic is going to be a t-score and not a z-score because sample deviations, sample standard deviations have a t distribution. So we're going to go ahead and calculate by the x bar, which is our statistic, minus the parameter of the mean of the population, which is our null hypothesis value, and then our standard deviation of the sample. Of course, the large sample conditions have already been cleared, and that means this statistic has a t distribution with an n-1 degrees of freedom. So we're going to go ahead and calculate the t-test statistic. Our statistic is going to be our mean from our sample of 15 batteries, so 33.9, and then a 30 is going to come from the null value of 30, which is the standard over lots and lots of time. And then we're going to divide that by the standard error, which is the standard deviation divided by the square root of n. When we do all that calculation, we end up with a t value statistic of 1.54, and it works the same way visually. Here we're looking for, here's a 1.54, and we're looking for this area underneath the curve to see if that p-value is less than 5%. So we're going to go ahead and find that 1.54. We look at our degrees of freedom, and the degrees of freedom is 14, and we're looking at the upper tail probability. And our value of 1.54 falls right in between 0.10 and 0.05. So that means that our p-value is somewhere between 0.05 and 0.10. So the p-value for this test is between 0.05 and 0.10, and then we have to decide what to do with that. So in this particular case, since the p-value is between 0.05 and 0.10, and we weren't given an alpha, so we can go with the standard alpha of 0.05, the p-value is greater than the alpha of 0.05. So we fail to reject the null. There is not convincing evidence that the new batteries have a longer average lifetime. So table B gives you a range of possible p-values for a significance. You can still use that information to decide if it's under your alpha level. And you can still draw a conclusion from it. But table B is a little more complicated in the sense that the degrees of freedom only go from 1 to 30 and then skip. And you got to pay attention to choosing a degree of freedom that is the next lower one, so you're sure that your conclusions are accurate. Table B shows the probabilities only for the positive values of t, so if you're finding the negative values of t, just use a symmetry to do that. So you can use a one sample t-test to decide if there's enough convincing evidence to reject the null, and same process that you're going to use in general for any significance test. You're going to choose a sample size n from a large population, and you have an unknown mu, so you're going to go ahead and test the hypothesis about your null assumption, and then you're going to go ahead and standardize the statistic and the extreme that we're looking for by doing the mean of the sample minus the null mean and square root of the standard deviation of the sample divided by the square root of n. And you're going to be looking if your alternative hypothesis includes greater than. If it includes lesser than, it's going to look below, and if it's not equal to, you're going to do a two-tail a two-tailed test, which in this case, if we had an alpha of 5, for example, 0.05, then we would align, it's aligned with a 95% confidence interval. So the connection between two-sided tests and confidence intervals is even stronger for means than it is for proportions, because of this part of the two formulas. You have that standard error of the mean as part of both formulas. And so these blue things, I'm going to state them as they relate to 95% confidence interval and 0.05 alpha, but you could just as easily talk about the 0.1 relating to a 90% confidence interval and an alpha of 0.05 relating to a 95 and a 0.01 relating to a 99. So I'm going to say these blue things with a 595, but you could interchange them. I just don't like the way this is written. It's confusing to me. So I'm just going to put in what can make sense to me. So a two-sided test at a significance level of alpha equals 0.05 and a 95% confidence level gives similar information about the population parameter. When you do a two-sided significance test that rejects the null, the 95% confidence level will not contain the hypothesized value. And if you do a two-sided significance test that fails to reject the null, that confidence interval will include that null value somewhere in there. So the null is going to be in there. And that's one way that they're very connected to one another.